All right, this is chapter 2, which talks a little bit about history of chemistry and how we developed the atomic theory, and then some atomic theory and a bunch of naming. Maybe a little periodic table, it looks like, down there. So, to start with the history, first dude that you need to know is Robert Boyle. He was way back in 1661, which was a while ago. He was the first dude who really got into measuring things, measuring the mass of all of the compounds that he was using, and doing experiments and keeping track of that kind of stuff, as opposed to the previous folks who were really more like alchemists and were just mixing stuff and going, "Where's the gold?" So he was really into measuring stuff. He was the first guy who said, that Greek idea of like 4 elements with water, earth, air, and fire, that's stupid. How about instead we say that elements are anything that you can't break down any further? So that was his definition of elements, and he actually discovered a lot of elements by breaking down stuff and using that as his definition. So that was Boyle. Next dude is kind of a funny dude named Stahl, and he in 1720 he came up with this theory called phlogiston theory, which is a pretty great sounding theory, in which things that burn because they have a mysterious substance in them called phlogiston, and once they have burned, they have lost all their phlogiston and therefore become dephlogisticated, and so they can't burn anymore. So for example, ashes are going to have like 0 phlogiston left because it was all in the wood, but now it's gone. And things that don't burn don't have phlogiston. So it's kind of trying to make sense of why things burn. The other part of that that's kind of great is that you could have, typical air is phlogisticated because normally you can burn things in air, but if you, for example, took some air and trapped it and burned a candle in it, you use up all of the phlogiston and it's gone. So now that air won't burn anything in it anymore because it's become dephlogisticated air.
Right.
So anyway, great, terrible theory, which got knocked out when Joseph Priestley, in 1774 discovered oxygen, and we actually understand burning better now because things burn in oxygen, and the observation about the candle won't burn again is true, but he misinterpreted it. So Antoine Lavoisier was a French dude. He was in the 1780s. He was also really into measuring stuff. In fact, he was into measuring stuff so much that he measured like all of the grams of everything that he ever did reactions with, and if he found that if he started with 182 grams of something, he always ended with 182 grams of something else. He was like, mass doesn't disappear. So he was the dude that did law of conservation of mass. Unfortunately, he was a mean Frenchie, and he got beheaded during the Revolution. Then you've got Joseph Proust, who was in the 1800s, and he burned a lot of things and found that if you took a compound and you burned it so much that it broke down into its constituent elements, it's not necessarily burning, but whatever it is that he did to break them down. If you did that over and over, we just zoomed in. If you did that over and over, you always ended up with the same ratio. So if you did carbon dioxide, for example, you would end up with, if you did a mole, you'd end up with 12 grams of carbon and 32 grams of oxygen every time. So the ratio was always the same. He's like, oh, that's cool. And so he came up with the law of definite proportions. Moving on from that, Dalton found that not only can you do that, but if you did something like separating, if you did carbon monoxide and carbon dioxide, which they weren't called that at the time, you could end up with 12 grams of, you could end up with, for every gram of carbon, you would have a certain amount of oxygen in carbon monoxide, but twice as much oxygen from carbon dioxide. And so he found that you could have several different proportions, but that they always had a simple ratio. So that would be a 1-to-2 ratio between those two oxygens. And that's the kind of thing that led him to think, oh, so there's something going on down at the small level with like countable items. It's a 1-to-2 ratio. One of them's here, two of them's here, which gave him the idea of atoms. And Dalton was the dude that came up with the, what's it called? The theory of atoms, the atomic theory, yes. So he came up with those 4 points of atomic theory. And the 4 points of the atomic theory are that everything is made of atoms, which are indivisible, and that's not entirely true. The second point is that, what's the second point? Dang it.
They're identical.
They're identical. Good job. The second point is that all atoms of the same element are identical, which is not entirely true. The third point is that that a compound is a combination, a simple combination of the different atoms of different elements, which doesn't have to be simple, so it's not entirely true. And the fourth point is that that chemical reactions are rearrangements of those atoms. So those are the 4 things that Dalton said, plus his law of multiple proportions. Moving a little bit off from that, there was another dude in France named Gay-Lussac, who was reacting volumes of gases with each other. And what he found was that you could react, for example, 2 volumes of hydrogen with 1 volume of oxygen and get 2 volumes of gaseous water out. And he didn't really know what to do with this, but then Avogadro realized that the reason that was happening is because equal volumes of gases have got the same number of particles, hence Avogadro's number. So this got us to our atomic theory, and a good understanding of number of particles, number of atoms exist. Then we start moving into, well, what are atoms made of? Which Dalton said they were not made of anything, but they are. So first dude to work on that was J.J. Thomson, no P. And he got a cathode ray tube, which is that glass tube, and shot a glowing line through it and was like, hey, what is that made of? And he was able to move the cathode ray up and down with magnets and up and down with electric fields and stuff. And so he figured out that the thing that was shooting through the tube was a negatively charged particle that was part of an atom. He named them electrons. And because they were particles that were part of an atom that were negatively charged, but he knew that atoms were neutrally charged, he said, okay, well then I guess the rest of the atom has got to be positively charged in general. So he came up with the plum pudding model, which is big spherical atom, mostly positive with little chocolate chips of negative electrons in there. So that was his atomic model. It didn't last very long, because it kind of got improved upon when we got to Bohr, but he's not in this chapter. The other thing that J.J. Thomson figured out about the electrons was that he was able to figure out the ratio between the charge and the mass. Now, when you have a ratio but you don't have either of the numbers, you're kind of stuck. You've got the ratio, but you're like, well, I don't actually know the real value of either one. Then along comes Millikan, who is famous for doing the Millikan oil drop experiment. Why do they call it that? And he had this big box, and what he did was he was able to make really, really small, misty particles of oil. And onto each of those oil drops, he put an electric charge. And he was trying to figure out the magnitude of the charge on these electrons. And because the oil drops were so small, let's say, for example, to make the numbers pretty, that the charge on an electron is 3. 3 negative, because it's negative, but the magnitude is 3. What he was able to find is that with those tiny, tiny little particles of oil with an unknown number of electrons on them, he was measuring the charge on each oil drop and getting numbers like 9 and 15 and 36 and 6 and, everything ending up being divisible by 3. And so he was able, and it wasn't actually 3, it was some ridiculous tiny small number, and so he had to do a whole lot of math that he couldn't just look at and go, oh, 3. But he was able to figure out the charge on a single electron. And then, since we had the ratio of the charge to the mass, we can go back and figure out the mass of an electron, which is very small. So there we've got the electrons. Rutherford runs with this concept of the plum pudding model and decides to shoot particles at them, which is what boys would do. So he shot some alpha particles, which is important to remember. An alpha particle is 2 protons and 2 neutrons. So it has a mass of 4, basically, and a positive charge. So they're going to get deflected away from positive charge and attracted towards negative charge. And he shot those particles at a really thin piece of gold foil, thinking that mostly they would go through and get close to the electrons and be slightly deflected, and then land on the detector that goes around behind it, and actually also most of the way around the gold foil. But what he actually found was that the alpha particles, many of them went straight through. Some of them deflected some, but some of them went like pew and shot off in the total other direction, which he thought was weird, and eventually decided that what that meant was that there was a very small positively charged center, and electrons were around the outside. So that was Rutherford working on kind of the concept of the nucleus. And that is the end of the history for now. There's a little bit more electron-y history in Chapter 7. So now we have the modern atomic structure. You have the nucleus, which has got protons and neutrons. The protons are positively charged. The neutrons are not charged. And it is very, very, very dense. Very dense. They're very squished. There's not much space between them. In contrast, you've got all this space around here, in which there are the electrons. The electrons themselves are 2,000 times smaller than a proton or a neutron. So a proton is way bigger than an electron. They are negatively charged. And people had been wondering for a long time, like, what is it? What causes elements to be different? Why are they different? And the answer is because of their electron configuration, which is related to the nucleus, but really the chemical behavior is the atoms fiddling with their electrons. So isotopes. If you remember, Dalton said that all atoms of the same element are identical. He was wrong. It turns out that there are, you can have the same element, and it's the same element by the fact that it's got the same number of protons. You're defined as an element by how many protons you've got. But you can have different neutrons. It can vary up or down just a little bit. So you can have, for example, sodium here, Na, with 11 protons. That's written on the bottom of the left side. But it could have 11 neutrons giving you a mass of 22, or 12 neutrons giving you a mass of 23. The electrons, as long as it's not an ion, are going to match the protons in order to give you that neutral charge. But the neutrons are different. Yawn. All right, so That's your very basic atomic structure. We're going to do more with that when we get to chapter 7. And now a bunch of naming. If you've got an ionic compound, and you need to remember that an ionic compound, which has ionic bonds, is usually comprised of a metal, which is from the left side of the periodic table, and a non-metal, which is from the right side of the periodic table, unless you're dealing with polyatomic ions. You can kind of stick those in instead. So for example, you can have lithium with 3 atoms of lithium and 1 atom of nitrogen, and that's the element's name, lithium, and then you use the stem of nitrogen, so you get but then you end it with "ide", so this ends up being lithium nitride. And the reason that you know that the formula is Li3N is because you know that the charge on lithium is +1 and the charge on nitrogen is -3, and you cross those down and that ends up canceling so that you've got 3 positives and 3 negatives so that it's a neutral compound. Don't do that. If you have something with an element that could have different charges, and that's going to be your transition metals, which are the dudes down in here. Many of those metals can have more than one option for a charge. You have to indicate that charge. So you go ahead and name this iron, because it's the first element name. Then chloride, that's what we learned up here, chlor from chlorine, and then you change it to ide. But this 3 here on the chlorine implies that the charge on the iron is 3+. You've got to include that in the name. So this is iron 3 chloride, and that's done in Roman numerals inside parentheses. You can also do it with the old-fashioned naming system, where "ic" is more and "us" is less. So iron 3 is more, so that's ferric. Iron 2 is less, so that's ferrous. For that to work, you have to have the charges for each of the elements memorized so that you know that iron comes with 2 and 3. Some of them come with 1 and 2. Some of them come, like vanadium has got 7 different charges, which is ridiculous. There's just a couple that get used frequently. Iron, ferrous and ferric, cuprous and cupric, stannous and stannic for tin, which is tin 2 and tin 4, plumbous and plumbic, which is lead 2 and lead 4, chromous and chromic, which is 1 and 2, or 2 and 3, something like that. I don't know. But there's just a couple that you run across more frequently. They typically just use the Roman numeral thing these days. And then you also have to handle polyatomic ions sometimes in the naming. Here you've got Mn, that's manganese, which is a transition element. So you've got to include your Roman numerals. So this is manganese 2, as implied by this 2 here. And then you have to name this, which means you have to have your list of polyatomic ions memorized. OH is named hydroxide, and it's got a charge of -1. Then covalent compounds. Covalent compounds are comprised only of non-metallic elements. So if there's a metal in there, you use this naming system. If there's not a metal in there and there's no polyatomic ions as well, you use this naming system. You have to have this list of 1 through 10 memorized. It goes like this: mono, di, tri, tetra, penta, hexa, hepta, octa, nona, deca. Those are the prefixes that you use to indicate how many of each element you've got. So for N2O, that's 2 nitrogens and 1 oxygen. So that's going to be di, nitrogen, and then you need to stick in the mon for oxygen. So this is monoxide. It's not monooxide. They'll drop vowels if they need to in order to make it not retarded. So because if they had another O, this would be monoxide. That would be fun, I guess. The other little rule that you have to remember is that you do not bother putting monos on front. So NO, there's 1 nitrogen and 1 oxygen. It is not named mononitrogen monoxide. It's just called nitrogen monoxide. Naming acids. the thing that you have to remember is ate ik, ite us. If your acid has got oxygen in it, which typically means that it's a polyatomic ion in it, again, you have to have your polyatomic ions memorized, so you have to recognize that NO3 is nitrate, and that NO2 is nitrite. So what you end up doing is you go, okay, nitrate, and then you remember the little rhymey thing, ate, ik, ite, us. It goes from ate to ik. So this is nitric acid, and this is nitrite, and then, okay, ite, us. So this is nitrous acid. So those are the ones that are a little bit harder to name. The ones that are easy to name are the ones without oxygen that are typically just your two element guys. You have to say hydro. So hydro, you use the stem of the other element, chlor, and ik. So this is hydrochloric acid. That's all the names. And then last little bit of periodic table stuff. Once they discovered a whole bunch of elements, what's-his-face Mendeleev decided it was time to put them in order and made a periodic table with properties repeating as you go down. So you end up with a column like the alkali metals in which all of the elements in that column have similar properties. They are all soft silver reactive metals that are fun to throw in water. The halogens are all reactive, crazy, deadly elements. The noble gases are all inert. They don't like to react. It's hard to get them to do anything. So you end up with guys that are very similar as you go in a column. So it periodically repeats the properties. A period is from left to right. So I might say, look in the fourth period, and you would go 1, 2, 3, 4. Okay, this one. The families are the columns. They're also called groups. And they can have numbers. Sometimes they'll do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. That's the modern system. So I can say look for group 17, and that's the halogens. You need to know the names of several of these. There's the alkali metals, the alkaline earth metals, the transition metals. I left off the bottom. The bottom, you've got your actinides and your lanthanides. You've got your nonmetals here in the top right corner above the zigzag. The zigzag is the line that indicates the semi-metals, also known as the metalloids, except for aluminum, who's a metal. I don't know why he's special, but I guess he is. And what else? The halogens are here and the noble gases are here. Yep. And then compounds is a group of atoms that's joined together by bonds. We've studied ionic bonds and covalent bonds. Covalent bonds are the type of connections between atoms where the atoms are sharing their electrons in order to get their full octet. If you have a single one, it's a molecule. So something that is a covalently bonded compound, if you can just pick up one of them, then you can have a molecule of water. Ionic bonds are different. The electrons are stolen instead of shared. And when the electronegative element steals the electron, it ends up being negatively charged, leaving the other dude positively charged. And so now they're attracted to each other physically because you have a negative and a positive dude near each other. The cation is the ion that loses its electron. The electron is removed, and you end up with a positive ion, which gives you the lame memory device, which is cats have paws. And then you've also got the anion, which is the electronegative atom. It's the one that pulls on the electrons real strong and rips them off of the poor guy who's going to become the cation. Results in him having an extra electron, so he's negative. Typically, cations are metals because they're wusses, and anions are nonmetals. because they are stronger pullers. When they combine together, you end up with an ionic solid. It can also be called a salt. Anything that is an ionic compound is called a salt. There's the regular salt, NaCl, but you can also have KCl or KBr or iron chloride or iron oxide, or like those are all salts. And don't forget about your polyatomic ions, which you have to memorize. Now I'm going to do the problems on the back of your notes. This is a good point for you to pause the video and go and do all of the problems yourself, and then compare your answers with mine. All right, question 1. Find the number of protons, neutrons, and electrons of a neutral atom of each of the following. And let's see, so we've got this one here. We've got CS 138, which is cesium. So let's find that sucker on the periodic table. Here's cesium with an atomic number of 55. So that means it's got 55 protons. So let's go back and get my pen. So we've got 55 protons. In order to find the neutrons, you have to subtract. And so that's 83 neutrons, 55 protons. Because it is neutral, you're going to have the same number of protons as electrons, so that's 55 electrons. All right, barium, Ba. Barium is here, which is number 56. Do I still have my pen? I do. It has 56 protons, so barium 136. In order to find the neutrons, you subtract, so that's 0 and 80. So 80 protons and 56 electrons.
80 neutrons.
Nope. Yeah, that's a good point. That's neutrons. Whee! All right, we've got La, which is lanthanum down here, number 57. Did I do a series in order? Looks like I did. Lanthanum, number 57. 57 protons and 80 neutrons. Dude, that's the same. And you're going to end up with 57 electrons in order to make it neutral with the protons. Here is lanthanum again. Lanthanum still has 57 protons. However, we have 83 neutrons and still have 57 electrons. And xenon, which is over here, is number 54. I did do a series. How about that? Xenon has 54 protons and 82 neutrons and 54, that's not a 4, 54 electrons. All right, the atom that has the same number of neutrons as 138, barium. I have to do that one too. Barium has 56. Boop. 2. None of them. Oh, yeah, no, this one is this one. Because that's 82 neutrons, 82 neutrons. So the answer is 130, xenon 136. All right. The formula. So copper, you need to remember the symbol is Cu. Copper 2 has got a 2+ charge. Phosphate is a polyatomic ion, for whom you must remember that the formula is PO4 3-. These guys are going to cross down, so you end up with copper, 3 coppers. You have to put this guy in parentheses because there are 2 of them. So that is Cu3 PO4 2. Magnesium has got a 2+ charge. There's magnesium. He's in the second column, so indeed he does. 2+ on magnesium. Bromine over here in the halogens has got a negative charge. Those are going to cross. So you end up with magnesium bromide with a 2. There's no 1 here. That's understood to be a 1. Sulfuric acid. Notice there's no hydro, so this is a polyatomic acid. It's ic, which means it came from, why do you do that? which means it came from 8-ic. So this is the acid made from sulfate. You have to have sulfate's formula memorized, which is SO4 2-, which combines with hydrogen, which that's a plus, which crosses to give you H2SO4. Carbon monoxide, you'll notice the mono, which means that we're talking about a covalent compound here. So that's, and you'll also notice that there's no mono on carbon, but that's normal. So 1 carbon and 1 oxygen. Ooh, that one was hard. Dinitrogen, 2 nitrogens. Pentoxide, O5. Hydrofluoric acid. Notice there is a hydro, so this is actually the regular type of acids, not the polyatomic kind. So that's hydro, which has got a plus, and fluorine, which has got a minus because he is a halogen. Crossy cross, you end up with hydrofluoric acid. And here are some dudes that need names. Here we have NH4, which you should remember the name of is
ammonia.
Ammonium. Yes. Ammonium. Ammonia is NH3. So this is ammonium, and then chloride. Here we have a nice acid, and this is SO3, which you have to have memorized is sulfite. So this is sulf. And then you have to think about 8-ic, us. A lot of people will put sulfus. That sort of makes sense, except it sounds retarded, so they decided to go with sulfurous. So that's sulfurous acid. Here we have a regular old acid with hydrogens and an element. So that's hydrosulfuric acid. Here we've got phosphate. So that's phosphor-8-ic acid. Did you just delete my dot? It's doing it again. All right. And we've got manganese. Manganese. And the thing about manganese is that it is a transition element, so you need to put his charge, 3. How did you know it was 3? Because this 3, thank you for circling and deleting my circle, was up here. So that's manganese 3. And then the SO3 is sulfite. Here we have a covalent compound with nitrogen and oxygen both being nonmetals, so it's covalent. You've got dinitrogen trioxide. Here we have Ti, which is titanium, which is a transition metal, so we need to point out that his charge was 2. How did you know it was 2? Because of this 2 that was up there. And then this funky dude, whose name is acetate, C2H3O2, is one of the polyatomic ions that you certainly know by now. Here we've got nonmetals, so this is tetraphosphorus. I know, right? And then we've got 3 seleniums, triselenide. Here we've got nonmetals, so this is boron. Why not mono? Because you don't do monos on the front. Tribromide. And we have another acid, which is based on the name of this guy, which is carbonate, 8-ic, so this is carbonic acid. The end. Derp, derp.